everyone. Today in this video clip, I'm going to go over 3 sections of our chapter 3, section 3.9, 3.10, and 3.11. So let's start with 3.9. It's about the related rates. It means what? The relationship between two rates of changings of two variables. Okay? So let me, how about give you an example. So you have, let's start with, how about the formula for area for circle. The area for a circle is 2 pi r squared. Is that right? So A here stands for the area, and pi is a constant. Pi is 3.14159 is a constant, and r is a radius. And you see what? Circle, center, radius r. What if you have a longer r? We have a bigger radius, and of course you have the bigger area of circle, right? And the changings of radius will affect the change of the area. And how are they related to each other? That's the question. Okay? Now, I want you to think of both r and a as function in terms of t. So when time changes, r means what? A function in terms of time, right? So with time is 1 minute, 2 minutes, or 1 hour, 2 hours, depends on the unit time. And with r changes, and what happened to the area. So area means what? The area with respect to the time t. Okay? So both a and r in our equation right here are functions. Okay? The variable is t. Okay? T. Usually t stands for time. So time passed by, all of those variables changing. Okay? So both r and a is a function in terms of time. So what happened if the time changes? If the rate changes with respect to time, what is gonna change? Okay? So the idea is this. You have RT, okay? So dr over dt is no more than r prime of t, right? And then dA over dt is no more than a prime, okay? So we want to find the related rates. We differentiate both sides. So in here I claim that the chain rule is going to be used for sure because both r and a are functions. So the variable is not in here, the variable is t. Okay? Chain rules, and you may have to use product rule, quotient rule, depends on the type of formula. But for sure, chain rule will be used. So, differentiate both sides. I have what? A derivative is dA over dt, or it's dA over dt. I was about to write a prime of t, which is the same, okay? I'm going to use limit notation in here. This is the master of the book, but you can use a prime of t, that's okay. Equal to 2 pi is a constant. Now r squared, you differentiate r squared, think of r as a function, so it's going to be what? 2r power roots times dr over dt, or you can write this way, 2 pi, right, a constant, and then r squared, derivative is 2r, and then times r prime of t. Same thing. Okay? So, how are the two rates related? The rate of change in the area is equal to, let's simplify this a little first, okay? It's 4 pi, 2 times 2 is 4 pi, times r times dr over dt. So the rate of change in the volume is equal to 4 times pi times the radius at that moment times the rate of change in the radius. Of course, same thing here, just different way to write it, okay? And that explains everything about this section, related rates. So when you guys do the homework, you guys gonna figure out the formula. If they talk about area, that's it. Talk about the volume, okay, figure out the volume. Let's talk about the volume for a sphere is what? V is equal to 4 over 3 pi r cubed, okay? And they ask you what? If the rate changes from the radius changing, how is the volume gonna change? So you differentiate both sides, you got what? dV over dt or v prime. Let me use the limit notation, okay? You what? 4 over 3 pi, and then times r cubed, derivative is 3r squared, and times r prime. Oh, I used dV over dt, so I should write what? dr over dt in here. So dV over dt is equal to that 3 cancel out, 4 pi r squared dr over dt. Okay? And in a particular example, they may give you the calculate dV over dt. If they give you r is equal to 5, say, centimeters, and dr over dt is 2 centimeters per second. So all you have to do is plug in the numbers. 4 times pi, and r is 5, so 5 squared. Dr over dt is 2. Plug it in. You have dv over dt. Or they may give you dv over dt. They ask you dr over dt. You do the same thing. Okay? The main thing is you figure out the formula, and then you differentiate both sides correctly. Okay, how about another one? I'll show you another one that you may have to use the product rules or the quotient rule. How about area of a rectangle? A rectangle, right? This is the length, and this is the width. The area of a rectangle is length times the width. So, if you change the length, the area is going to change. You change the width, the area is going to change. Okay? So, think of L here as a function of t. Length changes with respect to time, the area is going to change. Width right here as a function of t as well. If the width changes with respect to time, the area also changes. So, and again, the area is a function of time as well, because when the length and the width change, the area is going to change. So how do you find the relation between the rate of change in length and width versus the rate of change in the area? Differentiate both sides. dA over dt. Now I have to use the product rules in here because I have the product of two functions. Okay, keep in mind that one more time. L is a function, W is another function. So what? The product rules say what? The derivative product is going to be the derivative of the first. So dL over dt times W. This is L, not E. L. And the derivative of the first times the second plus dWs over dt times L on the first. And of course, if they give you a number, you plug it in, you have the answer. That makes some sense here. Okay. More formulas. It's pretty much the same thing. I keep repeating the same idea, just show you a couple of formulas. You may have something called the volume of a cylinder. So how do you find the volume of a cylinder? A straight up cylinder. This is the radius r, and this is the height h. And the volume of this thing is what? Volume is area times the height. So area is pi r squared times the height h. Okay, this is the area of the bottom, pi r squared, circle, times the height. You have the volume of that cylinder, and you see this in the formula right here. The volume will be decided by the radius of the base and the height of that cylinder. Okay, so one more time, r is a function of the time. H is also another function of the time. Time change, height may change up and down, longer or shorter. Time change, the radius move longer or shorter. Of course, affect the volume. So in this section 3.9, we try to show you the relationship between the rate of changing of those functions. So dV over dt, see, dV over dt means what? The rate of change in the volume. Pi is a constant, put outside. Now we have product of two functions, r and h. We have to use the product rules again. So the derivative of the first part is 2r times dr over dt. See, r squared, the derivative is 2r dr over dt. Plus, the derivative of the second part is what? dh over dt times r squared. And everything times pi. Okay? And of course, they gave you numbers in your homework. I will stop right here for this, but in the homework, this is like the core part, the backbone of your problem, the main thing. Plug in the numbers, you have the answer. Okay? There is a very typical problem that I've seen over and over in business calculus, in regular calculus. They have this. You have a ladder that leans against the wall. This is the wall. Okay? You have the ladder. The length of the ladder is L. Okay? So of course this is X and this is Y. And friction is not strong enough to hold the ladder still, and it's going to be sliding down. Okay? Sliding down means what? X is going to move in this way. This point right here is going to move in this way with some speed. And the point down here, the point Y is going to be moving down this way. How do you find the relationship between the speed, the rate of change for the X point and the Y point? So we set up the equation, same idea. Pythagorean theorem say what? x squared, this is x, and this is y, plus y squared equal to L squared. Is it right? Two sides square, square of two sides add up equal to the hypotenuse square. All right. Now differentiate both sides. 2x squared, the derivative is 2x. dx over dt is x prime. Okay. One more time, x here is not the variable. Okay. The variable is t. X is the function in terms of t. X keep changing the time. And then y is another variable in terms of t, another function in terms of t. So this is 2y dy over dt is equal to, L is a constant, so L squared is derivative 0. Divide both sides by 2, you got what? X dx over dt plus y dy over dt is equal to 0. In other words, x dx over dt is equal to negative y dy over dt. But x is moving far away from the origin, y going to move closer to the origin. Move in the opposite direction. That's why you have a negative sign right there. Okay? And if they give you the value for dy dt or y or x, plug them in. Whatever they ask, you have the answer. Okay? That was the whole thing about 3.9. And I got every single question in this section. I'm going to go through the same steps, same frames that I'm showing you right here. Set up the formula correctly, differentiate the equation correctly, then you plug the numbers in. You have the answer. All right. Let's move on to the next section, 3.10. What is it called? Linear approximation, I think. Okay. Linear approximation. Okay. So the idea is this. We have a function, f of x. We want to approximate the value of the function f of x at some point. Okay? F of a is equal to how much approximately. Of course, if you know the answer, then you're good. If you don't know how you approximate, the idea is this. So you have a function. Okay? This is my f of x. I don't want to know the entire function. But you say if I only know like one point, right here, linear means this. Let me try to draw it better so it's easier for me to graph. X-axis, y-axis, you have a function right here. This is A, okay? You want to approximate f of A right there. Linear means what? If you look at the function closely, just a little piece of the function right here from here to here. So that curve from here to here is very, very close to the tangent line at the point A right there. Point A right here, this is f of A, by the way. F of A, okay? So in other words, the little curve that we see, that piece right here, is very close to that tangent line. Not the same, of course, approximation. So that curve is approximated by that little piece of the tangent line. Okay? That's what they mean by linear approximation. So we're going to represent that little curve from here to here by that little line segment from here to here. What do we know about the line? This line is called the line L right here. The line L got a slope is f prime of A. Remember, we learned about the derivative of the function at the point is the slope of tangent line. So the slope of the tangent line is f prime of A. And it goes through the point what? A f of A. And we have the point. A f A. So we have the slope, we have the point, and we can calculate the tangent line. And that tangent line is a pretty good approximation for that little curve when we have a point very close to, we have the points are very close to the point A right here. Again, they're not the same, okay? The curve may be a little bit off the line, but if you're looking at just small interval, pretty much the same. So how do you find the line if you have the slope and the point? We learned that in college algebra. Let's call the line L, okay? Line is what? Slope times x minus a, and then plus f of a. This comes from this. y minus y0 equal to m times x minus x0. Okay, this is f of a, this is a right hand slope is f prime. And I have the formula. So, it's all in this section is this. When x is close to a, say a is right here, x is very close, around here, x is very close to a, then the curve can be approximated with the part of that tangent line close to that curve, then f of x is very close to L of x. Okay, the function when x is close to a, okay, f of x approximately equal to L of x, which is L of x is right here, f prime of a times x minus a plus f of a. Okay, that's called linear approximation. Question: what is it good for? I can show you an example of it. Say I have a function f of x equal to square root of x, a simple one. Okay, example. And I give you, say, as you know this, I don't really need to give you. F of 4 is square root of 4, which is equal to 2. Is that right? Can you approximate f of 4.05? Approximately equal to what? Nowadays we have calculators, so this is piece of cake, but we try to show you how to do linear approximation, okay, without calculator. All right. So what do we have? F of x equal to square root of x, which is x to the 1/2. Is that right? So f prime of x is equal to 1/2 square root of x. Cool enough? So I apply what we learned right here. F of 4.05 is, I think of 4, around 4, right? So 4.45 is very close to 4. So A is here is 4. Okay? So this is what? F prime of 4 times 4.05 minus 4 plus f of 4. You see what I'm doing? I'm using right here. This is f prime of 4. Okay? This is 4.05 minus 4 plus f of 4 right here. So f of 4.05 is approximately equal to f of 4 plus a little bit more. Okay? So how do we calculate this? F prime of 4 is right here. F prime of 4 is 2/2 square root of 4, which is 2 over 4, which is 1/2. So this is 1/2. 4.05 minus 4 is 0.05. F of 4 is 2. You plug it in, you got f of 4.05. It's pretty close. Okay? You see the idea of approximation? If you know a point, and you can approximate the point of the function close to that point. That's the idea. Here, I know f of 4. Then I can approximate f of 4.05. Similarly, can I approximate f of 3.999? Yeah, same way. F of 3.999, okay, is approximately equal to f prime of 4 times 3.999 minus 4 plus f of 4. Same idea. This is 1/2 times negative 0.001, I think, and then plus, what's that, 2 right here? So you know square root of 2, square root of 4 is equal to 2, then square root of 3.999. You calculate this number, it's going to be 1.9 something. Okay. 1.9 something. Okay. And here, you know that square root of 4 is equal to 2, f of 4, right? So f of 4.05 means square root of 4.05, I mean, is equal to 2 point something. Okay, that was the idea of linear approximation. And you guys can apply this technique to approximate the numbers, the value of a function. If you know some other values of the function pretty close to the value that you want to approximate. Okay? And I claim that all the exercises are going to go around this formula. And that is the end of 3.10. Okay? So the idea is not too complicated. You can go back and watch the video clips, make sure that you get it. The main point that I try to bring you is spend some time and practice, okay? That point that I cannot help you with, you need to practice. Have any question, have any difficulty, please let me know. I'll help you do some work, okay? Next, I'm going to talk about 3.11. Now it's completely different from the other two sections that we covered. 3.7 about hyperbolic trig function. So I'm just showing you all the formulas, okay? And you guys can just practice the formula. They just give you basic formulas and try to practice. Play around with it and remember the formula. That's all. We learn trig on circle. Now we learn trig on hyperbola. So we call it hyperbolic trig function. Hyperbolic function. Hyperbolic functions. Okay. So we're going to define our new sine and cosine. We call hyperbolic sine and cosine. We define hyperbolic cosine of x is equal to e to the x plus e to the negative x over 2. Just a function. All right, we define it this way. Okay, think of it as an f of x. It's cosine. We call it the function. It's cosine hyperbolic. Cosine with an h right there means hyperbolic cosine. E to the x plus e to the negative x over 2. And we define another function. Hyperbolic sine of x equal to e to the x minus e to the negative of x over 2. Okay, you know e, right? It's an exponential function. So we got a lot of interest in coming up. Now we have cosine and sine. So hyperbolic tangent of x is defined by hyperbolic sine over hyperbolic cosine, which is e to the x minus e to the negative x over e to the x plus e to the negative x. You do a simple algebra in here. And similarly, hyperbolic cotangent of x is cosine over sine, hyperbolic of course, e to the x plus e to the negative x over e to the x minus e to the negative x. Okay? And I think we have two more trig functions in here. Cosine, then secant, hyperbolic secant of f. Secant is reciprocal of cosine, so 1 over cosine, which is 2 over e to the x plus e to the negative x. And the last one, cosecant, hyperbolic of course, is 1 over sine, 2 over e to the x minus e to the negative x. Those are the definitions of the hyperbolic trig functions. Okay. Now we come up with some trig identity, and you guys are gonna relate it back to the our regular trig identity using circle. This one has its own advantage. Okay. We have hyperbolic cosine square of x minus hyperbolic sine square of x is equal to 1. Okay. How do we prove this? Square this up, square it up, okay, and do a subtraction, simplify, you have this. Okay, and if we divide both sides of this equation by, say, cosine square, I got 1 minus tangent square. See, divide both sides by cosine. 1 divided by cosine square, I got 1, and tangent square. There's 1 over cosine square, which is secant. Oh, I'm missing c. Hyperbolic secant square of x. Similarly, if you divide this equation both sides by sine square, I got hyperbolic cotangent square of x minus 1 equal to hyperbolic cosecant square of x. So forth and so on. Okay. The book gives you the whole set of formulas in one, so I'll just throw out on the board and just try to practice. Okay. In Calc 2, you guys see that many integration technique problems turn out that if you know hyperbolic trig function, it's going to be easier for you to do the integral problems relatively compared to the regular trig function. Of course, you can do the normal trig function, circular trig function. It works as well, but this one is going to work faster on many problems. Okay. Talk about even or odd functions in here. Cosine is always an even function. Even function means cosine of negative x equal to cosine of x. And sine is odd. Sine of negative x is negative sine of x. So cosine is even, sine is odd. So reciprocal of even function is still even. So secant hyperbolic of negative x equal to hyperbolic secant of x. And then this is also odd, so cosecant negative x equal to negative cosecant of x. Okay? And both tangent and cotangents go with odd functions, so it's still odd. Hyperbolic tangent of negative x equal to negative hyperbolic tangent of x. Hyperbolic cotangent of x, so negative x, I mean, equal to negative hyperbolic cotangent of x, because tangent, both tangent and cotangents are the fraction of sine and cosine. Odd divided by even is still odd, and even divided by odd is still odd. Okay, that's about even or odd function. Okay, now the sum difference formulas. Cosine, hyperbolic cosine of x plus y is equal to cosine x, cosine y, plus sine x and y. Yes. Hyperbolic cosine of x times hyperbolic cosine of y plus hyperbolic sine of x times hyperbolic sine of y. How to prove this? Use a definition. Okay, I'll give you a hint. I'm not going to prove the whole thing. It's considered as a homework for you. Cosine of x plus y is e to the x plus y plus e to the negative of x plus y. Remember definition? E to the x, e to the negative x over 2. Right, so this is x plus y, so x plus y and negative x plus y over 2. Okay, and you try to prove that this left hand side is going to be equal to what? Cosine of x is e to the x plus e to the negative x over 2 times e to the y, e to the negative y over 2. This is what? Sine is e to the x minus e to the negative x over 2 times e to the y minus e to the negative y over 2. You multiply them all out, you combine the right term, you simplify the right hand side, you're going to get the left hand side. And this is a very good exercise for you. Okay, but anyway, this is a formula. And I'll give you the hint to prove right here. And then sine, hyperbolic sine of x plus y is equal to sine cosine, okay? Sine x cosine y plus sine y cosine x, all right? The way to prove this one is exactly the same as the way to prove for the upper one right there. Now let's talk about derivative. There's a lot more formulas, but I'm just giving you whatever the book gives you, so you don't need to learn more than what you need to do your exercises. Hyperbolic sine derivative, very similar to circle trick, right? This is cosine. No parentheses. Derivative of sine and cosine. Now here comes the interesting thing. Derivative of cosine is just sine. Okay? No more negative. This one. How to prove this? Same thing, let's do cosine right here. Cosine is what? E to the x plus e to the negative x over 2, right?